Okay, so last class we started talking about the streaming model of computation, which, as I said, is kind of arises in most big data systems. And we started with a toy problem, which was approximate counting question, and we saw one solution to it, which was Morris's algorithm. And then we introduced two important questions within streaming algorithms. One is the heavy hitters problem, then the related frequency estimation question. And our goal today is to give algorithms for frequency estimation. And as we argued last time, if you can solve frequency estimation, then you can basically solve the heavy hitters problem, right? So we'll solve the two questions, and along the way we'll also introduce this important idea of sketching. All right. And one announcement, I have to cancel office hours today due to some unforeseen circumstances, but instead I'll hold office hours tomorrow and Friday from 9:30 to 10:30. So if those hours don't work, let me know and we can still figure out something. And what else? Oh yeah, I also wanted to say that the official feedback will open this week. Right, so just say. So the CCLA feedback links I think will open this week. We collected some feedback in the middle of the quarter, but if you can provide more feedback towards the end, that would be helpful for the next iterations of this course and for what can change. Okay, I think it's going to open Thursday or something like that, 27th. Yeah, and it's closes next week, end of the next week. Okay, so what was the frequency estimation question, right? So the input was some stream, x1, x2 to xn, each coming from elements from 1 through n, and you process this stream. You want to process a stream, keep some internal representation, and then someone asks a query, what is FA? Okay? Someone gives you a query which is an element A in this space, 1 through m. And their goal is to compute an estimate, right? Compute an estimate so that this error is small. Okay, that was the question. Okay, so what is the algorithm that we're going to look at? So the algorithm is, it's again, everything is based on counters, right? Because frequency estimation is really just a counting problem. But what we'll do is to keep the counts in a very clever way. So the Misra Greece. Okay. So the idea is I want to somehow keep track of the top k items so far. Think of some parameter k, which is going to be basically like 1 over epsilon, but we want it to be an integer, right? So imagine k was 2 or 3. So I want to keep track of what are the top 2 items in this stream. What are the items that are occurring the most often? Okay. So what we'll do is to keep track of k counters. These are meant to be the set not like, it doesn't mean C0 is the most occurring, C1 is the next most occurring, and so on. It's just meant to be the set of top k items, the counts. And we also keep track of k items, k item names, let's say. Right? So A0 is going to be one item, and C0 is the count of that item in the stream. That's that's the intention, at least. Okay? And we'll initialize all of these counters to 0. We haven't seen anything. And all of these to just like null. And we haven't seen anything, just let me put the symbol perp for that. Okay, and now whenever you see an item, like when you process a new item is thrown at you in the stream, you want to update these counters in some way. So how do you do that? And that's where the cleverness comes in. For each stream element, you have to do something. So I see x of I, and there are various cases, right? So if my intention is that these are the top k items, what should I do when I see an element? Any suggestions? Think of the most, sort of start with the simplest ones, and then we'll take it from there. So we see xi. What should I do when I see xi? Any suggestions? Okay, so let me give some prompts. So if xi is in A, okay, so let's think of this array of items A, A0, A1 up to ak-1. If I tell you that this item is already in my array, what should I do? Any guesses? What would be the natural thing to do?
Just increment the counter for that item.
I'm able to hear you, Kirti.
Oh, can you hear me now?
That's weird. Hold on. I think you're muted, Kirti.
Can you hear me now? Or
I could hear him.
Yeah, for some reason I can't hear you, but I see what you said, which is increment counter for that item, right? We are thinking that it's one of the k most frequent items, and if you see it, let's just increment it and see what happens, right? So increment corresponding counter. Okay. If it was the second, if it was A1, then just increment C1 and so on. Right, that's the most natural thing to do. And what about the case where, it's a new item? So we are looking at the top k items, but now I see something which is not one of the top k things. What should I do then? Any suggestions? So let's think of what happens at the beginning, right? When at the start of the algorithm, I haven't seen any items. So far, the array is basically just null pointers, the counters are all set to 0, and I see a new item. It is definitely not in the array, right?
Add a new item to A.
Hold on. I think I'm unable to hear anybody for some reason. Can you hear me? Okay, but why am I unable to hear you? Okay, so if this item is not in the array, then what should I do?
So add xi to A.
Right. So I'd like to add, but the size is limited. There can be at most k items, right? So there are two cases here, right? If there is space in A. So let's say, you have k slots, but one of them is still empty. There's no pointer there. There's just a null symbol. And then what you said makes perfect sense, right? So, i.e., okay, so there is a null symbol somewhere. Add xi to that position. Set corresponding counter to 1. Okay? Like for instance, when you start out, everything is null, everything is empty. So you see an element, you just add it to one of those positions and set the counter to 1. I've seen one element of this item so far, one copy of this item so far. Okay, but what do you do if there is no space? Meaning, all of the positions in A have an assigned element, all of them have counts more than 1, but on the other hand, now I'm seeing something new, something not in these k things. What should I do then? Any ideas?
Merge the item in A with the number of counts.
Can you say it again? Sorry.
Like merge two items if they have some counts.
Right. So that's a good suggestion. Like, somehow, maybe if there is one item in A which has more copies that we've seen so far, we should do something. But the point is, like, how do you merge the items, right? We want to keep track of only k names at any state of the algorithm because we don't want to increase the memory. So what can we do? Any other ideas? Okay, so it's kind of a little tough to motivate what they did, but it's a very clever solution. So their reasoning was, maybe this item is going to be the most frequent in the future, right? So we can't just discard it. Like, you can't say, okay, the previous items, they're all more frequent than this item, so I'll just forget about it and keep the state of the array as is. Because then I'm not keeping track of how many times I've seen this item, and in the future, that will cause me problems. So they had this ingenious idea that, if there is no space and there is a miss in the sense that the new item is not the item that I'm currently seeing, is not in my array A, I'm going to penalize all the items in the array. In the sense that you're going to decrement counters I am going to decrement all counters by 1 and kick out all items with count 0. Okay, we'll just do a trial run soon, but Does this make sense? Basically, whenever I see a miss, i.e. there is a miss, okay, meaning somehow the new item is not in my array, then I decrement all the existing counters by 1, and if something reaches 0, I throw it out. In some sense, it's saying if you know all the things in your array have exactly count 1, they should be equal to the new item, because you know it's just a single copy so far. So I'm just going to erase all of those. Does this make sense? I mean, it's kind of it is a non-trivial idea, I think, very clever solution. Okay, but let's see what what this entails, right? So let's do an example. Okay, let's do an example run where I set k equals 2. I'm going to keep track of 2 counters, and that's it. And my stream is maybe whatever, A, B, C, B, C, A, B, C, whatever. I mean, it doesn't matter what the stream is, we'll just see what happens, right? And let's keep track of, this is C, this is A. So initially I have 0, 0 and null, null, right? This is start. And now I start processing the stream. So I see this element and what happens to the counts? So I'm going to change the counts. Now I see the element A, so I'm going to increase 1 counter to 1 and make this A. Okay? Fine, right? And then I see the next element. What happens to the counter? You know, you just increase it, right? This becomes 2A, step 2. Right? You know what, actually let me draw them horizontally. That makes more sense. Okay. All right. And then I see one more element and things change. I get 3, 0, A, and 1. Right? And so far, I haven't seen a miss after the first round. Everything I'm seeing, you know, it's kind of like, I'm seeing a miss, but there is an empty space. So I'm just adding it. Now what happens? I see B. So the A part stays the same. So B is not in the array, but then there is still space, right? There is a null space there. You know, there is an empty cell in my array. So I just put B there. Okay, but now when I see C though, what happens? So what happens when I see C? Can anybody tell me?
So you decrement A and B, so you get 2, 0, and then B gets kicked out,
Exactly.
and then you put in C with
No.
count 1?
No. Right? Because somehow you're kicking out B means that you only saw B once, right? And C also you only saw once. You don't want to prioritize between the two yet. But the idea is that now if you start seeing C, it's going to take B's place, right? So, I mean, that's how the algorithm is going to change. Like, next time it's going to be, maybe one change here.
Would this mean that there could be edge cases where, like, if the algorithm stopped at like an inconvenient time, like you'd have a bunch of zeros and wouldn't know which items were in that tie for the kth place or something like that?
Yeah, so there could be situations like that, but we'll see that, it only happens in very rare cases, and in those cases, you're still within margin of error, as we'll see. Okay? So let's see. So now, I'm putting B back, right? I get to A, B, and then C comes in. Right? You can see A is also decreasing, right? Isn't that cool that A is also decreasing? Okay. And then you see A, so A increases, you get 2A, sorry, B should be picked out here. I see A, and this stays the same, and then I see C, which makes it 2A, 1C. Okay, and then I get 2A, 2C. Okay, hope that makes sense. Basically, this process of decrementing all the counters and kicking things out is counterintuitive, right? But the idea is that somehow, if you see a miss, that means that the other things, you want to account for how many times in the future you might see things again. Okay, does it make a little bit of intuitive sense of what the algorithm is doing? Okay, so that's how you process the stream, right? But they say, in the streaming setup, we have two parts. Somehow you process the stream, and then there's the querying phase. Someone comes and says, hey, here's my element A. Can you tell me what its frequency is? So how do I answer that? So query. So the input is an element, A, which is from 1 through M. And what should I say? What should I output for the frequency? Any guesses?
I guess if it's not in the table, we should just say 0 or
Right?
something.
Yeah.
And
If
then
it is not in array, then output 0. Right, so this is our estimate for the frequency of that element. And if A is in the array, what should I do?
would you want to do the count? Oh, the count over n. Okay.
Right, I'm just going to output the count divided by n. Right, so let me write it properly. So count of that element divided by n, and this is our estimate f tilde n. Okay? And I mean the query part I think is you're doing what is most intuitive really. Okay? The processing part is where somehow there was something clever about it. Make sense? That's what they suggested. This is like maybe almost 2-3 decades ago, the algorithm. A very simple one. Now let's see what this tells us. I mean, what is this giving us in terms of frequency estimates, right? It seems like it could be very bad off. Like you already pointed out there are some edge cases, maybe where you just output 0 for everything, right? So how is that even a meaningful answer?
But that's only possible, it seems like, if everything occurs like with an epsilon frequency or something.
Right, exactly. So that's the point. Like somehow, if an item gets kicked out, if everything is kicked out, that means that there are some multiple items with high frequency, in particular, or comparable frequency, which in particular means that none of them is pretty high, as we'll see, okay? And so the claim really is that for all A, f tilde A as computed above, okay, minus fa. Well, okay, so let me ask you something, right? So I want to compare my estimate to the true frequency. How do you think this relates to the true frequency of the item? Tell me one relation between the two. Which can be higher, lower, or can they change?
It's at most the true frequency.
Right, it's at most the true frequency, right? Because you increment the counter whenever I see the item, but sometimes I decrement it. So I'm definitely not going to have the final count be more than how many times I see it in the stream. Right, I only increment it by 1 whenever I see it. Okay? So this is true frequency, i.e. I such that xi equals a divided by n. Okay? But, I could just output 0 for everything and satisfy this guarantee, right? So that's not a meaningful answer. The lower bound is the nice thing, which is that it's okay. We'll see that it is close to the actual frequency up to this additive error of 1 over k. So for instance, if I wanted the additive error to be like 0.1, I just need to keep track of k equals 10. So just 10 items. Okay? Make sense? Alright, so that's the claim and we'll prove it in a second. But before going on, let's check what is the space and time complexity of the algorithm. Right? How much space do we need? I mean, the reason we are doing all of this is to understand space, to minimize the space. Okay? So how much space does our algorithm need? Well, if you go back to it, we had to keep track of k counters, right? C0 through ck minus 1, A0 through ak minus 1. So how much space would that need? How much memory do I need to write down each counter? Maybe...
Like log n?
Yeah. So each counter is log n. And how about each array element? How many bits of memory do I need to do that?
Like the A, B, C, those things?
Mm-hmm.
Maybe only log K?
Log m.
Okay, okay.
I need to store the name, right? You know,
Okay, yeah.
I need to store down like the IP address number of bits. Right. So it's basically for each cell in array A. Okay, I mean, kind of a simple bound. We have k cells. You know, each cell, each counter can take at most log n bits. Each name can take at most log n bits, and that's it. Okay. And in terms of update time, so update time is basically like, you know, you're saying, well, I tell you this element, I have to find if it's in the array, and then I have to increment its counter. You can use hash tables for that. Or basically use dictionary data structure. So this part is very fast. You know, basically when you don't see an item, you might incur O of k steps because you have to decrement all the counters. But you should use a dictionary data structure. Like you just have to do a fast lookup, you know, then change a counter, check if it's in the table or not. That's exactly what a dictionary data structure will do. You can use anything that you want: binary tree, associative array, any standard thing. And query again is just a lookup. Okay, so everything is very fast, the memory is very small, it's logarithmic. Whereas we saw that the naive solution was like, you know, linear in this length of the string. Okay. All right, so the only thing left is to understand why this is true. Like, you know, why is it saying that somehow magically the estimate that we're giving satisfies this very accurate count? It's at least something, right? So let's take a 5-minute break, and when we come back at 10:40, we'll go into why this is true, and it's actually not that complicated, as we'll see. All right, let's start. Okay. So we want to show this claim, right? You know, the upper bound is kind of not too complicated because, you know, we only increment. Okay, so just for notation, let NA be the number of times number of not items but times A occurs in the string. Okay. Then what we are saying is that, yeah, well, you'll see what. Okay. Now, the next step is to count, to kind of get a lower bound on the count that we store for that element A. Right? So how can I do that? Now, the proof, as I said, let's call the algorithm, or let's say misses when we do the decrement operation. Okay, so, you know, when their item is not in the array and there is no space, that's when we have a miss, and that's when we do the decrement operation. All right, so the way to compare the things is the following. The total number of increments done is, so how many times do you increment a counter in the entire run of the algorithm? Let's go back to the algorithm, and basically we increment the counter in either when we make it from 0 to 1 in this A, or here, right? So in both of these cases we can increment the counter. So what's the relation between the number of misses and the actual number of increments that we do? Any guesses? I want to say that whenever we don't do a miss, we increment a counter, right? That's exactly what the algorithm is doing. So the total number of increments done is n minus number of misses. Whenever we don't have a miss, we increment the counter. Or increment a counter. That's what it means. On the other hand, each miss decreases lots of counters, right? How many counters do you decrease each miss? Each miss decreases all counters by 1. Okay, somehow each miss leads to a penalty of k decrease in the total counts, right? So imagine I'm tracking the sum of all the counts in my current structure. Whenever I see a miss, this sum of all counts decreases by k, right? And each miss decreases all counters by 1. So it implies sum of all counts. Okay. Is at most so whenever I encounter a miss, I decrement the counter by k, decrease the counters by k. Right? Actually, this is equal to. Does this make sense? Whenever I don't have a miss, I increment it by 1. So I added n minus number of misses. And then whenever I encounter a miss, all sum of counts decreases by k because I decrease each one by 1. So sum of all counts is exactly this much. Right? Any questions about this? And we know that 0 is less than or equal to this. Sum of all counts is always positive. We never decrement a counter when it is 0. We only decrement it when it's at least 1. Right? So all counts are always non-negative. So sum of all counts is non-negative. So we have this scenario. So this implies that number of misses is less than or equal to n divided by k plus 1 actually. So I think this should have been k plus 1. Okay. Does it make sense? So somehow intuitively, a miss is a bad operation, right? You know, you're not finding the item in your top k thing, so maybe that's kind of a bad thing. And this analysis is saying the number of misses your entire algorithm will incur is at most n over k plus 1. Right? Okay, any questions about this? So now I want to say that this is enough to tell me that my frequency is pretty good. So this implies that count for A is at least number of times A occurs. So whenever A occurs, I either increment it or I decrement it when there's a miss, right? So the number of times A occurs minus the total number of misses. Maybe unluckily every miss led to a decrement in the counter for A. So this is at most n over k plus 1. Even if unluckily every miss led to a decrease in this counter, even then the total decrease is at most n over k plus 1. Okay? So this implies that f tilde A, which is count for A divided by n, is at least fa minus 1 over k plus 1. Okay? Any questions about this? So that's the full proof. I mean, it's a very simple analysis, right? And the cleverness here is that somehow you can control the number of misses that your algorithm does, just because every time you do a miss, you decrement the total sum by k, and it's never going to be negative. Okay, so that's a very simple way to keep track of the frequencies in your stream with only k times log n plus log n bits. So now this is great. So let's do a quick summary. Need, or it's not need, but k times log n plus log n raised to space to get error 1 over k plus 1. Okay, so as I said, we should think of k as being something like 1 over epsilon. If I wanted 0.1 accuracy, additive accuracy, then I would set k to be something like, maybe 9, and then I just say 9 log n plus log n. Okay, and you can also see that this is a very practically efficient algorithm. Okay, so this pretty much, is kind of as good a solution as you can hope for frequency estimation, and it's a deterministic algorithm. The guarantee always holds. But there is one small catch, which is what the next algorithm is meant to address. Okay, so what is that catch? So remember, for frequency estimation, our goal was to count, and also to solve the heavy hitters problem. I want to find out what are the top 100 searches, let's say on Google. What are the 100 most frequent items, on Amazon, right? Things like that. So going back, our original goal. Top 100 searches on Google. Okay, someone comes and says, what are the top 100 searches on Google, over the entire time? How do I answer that? I know I can keep just track of this, can keep running this Mr. Gris algorithm for every search, and that will be it. So top 100 products. Top 100 movie downloads. Okay, and in all of these, we're not really interested in the exact answer, right? So we're interested in this approximate answer where the underlying belief is that somehow, there are items which really dwarf like the low end of the occurrences, right? There are some 100 items which will occur at least some 0.01 fraction of the time, and then somehow you want to take care of those, identify those. Okay, but now what if you're trying, you're keeping track of all of these things, but suddenly someone asks, I'm not just interested, you ran this algorithm, you process the stream, you're interested in top 100 searches on Google, but now I want to add a qualification. I want to refine this search in US. Someone asks, okay, what's the top 100? What are the top 100 searches in the US? Someone can ask even in, let's say, in Texas versus in California. That can really show differences, right? In the top 100 searches in Texas, even a specific time, let's say in the last year during the pandemic, would be very different than the top 100 searches within California. And if you process the stream already, how can you go back and get these refined answers? Someone says, okay, what if I'm interested in not just the top movie downloads, but in US, again, maybe by genre, by length, things like that. How can I sort of group things, ungroup things, and find out how to aggregate even streaming statistics, right? How can I do that? Any ideas? Let's say someone comes and says, let's stick to the products example, right? You're searching for top 100 products on Amazon, but now I say top 100 products by department. And this is something that you see often on Amazon, right? By, maybe movies, books, toys, clothes, electronics. There's a different department, right? And then you can also have this kind of hierarchies, right? Books and toys are maybe one hierarchy. Movies and music is in entertainment. Okay? Somehow it's you have all departments, and then you have some hierarchical sort of categories, right? So there's entertainment, electronics, maybe toys, clothes. And here you have men, women, maybe pants, shirts. Here maybe you have kids and toddlers. Here you have laptops, cameras, movies, music, anime, whatever, TV. You can just imagine, you really do have these categories, right? And you do have millions of items coming across in each of these categories, right? What would be a solution if, I might want to know what are the top 100 categories in each of these things. What are the top 100 in anime, top 100 in TV, top 100 in music, laptops, and every kind of, every node here. How can I do that? What would be the most straightforward solution?
You could just do it for each of the base categories, and then you can calculate the ones above the tree.
All right, so that would be great. right? If I could, it seems like if I want to do anime and things like this, I should at least keep track of the base, this sort of least indivisible units. Okay, let's say I do that. That sounds great. But now, if I keep track of anime and TV, what are the top 100 things in anime, top 100 in TV? How can I combine them to get the top 100 in movies? How do I know? I'm only keeping track somehow of the relative counts, right? How do I aggregate them to get something from movies? What if I have like dozens of different things and I need to aggregate them to get something globally? Maybe most of the downloads are anime, and then in that case, even if something has a small count within this subcategory, when you go up, it might still be higher than the top 100 in TV.
But don't we know, like in the algorithm we just talked about, we use n to calculate things. So we know like the total number of animes, right?
Right. So you have to keep track of all of those things again, right? So n was just one stream length, but now if I have dozens of categories, you have to keep track of how many anime I actually saw, how many TV I actually saw.
So do we want to avoid doing that? Or?
Right. So I mean, not necessarily, but maybe we can ask, what if there is a more streamlined way of combining things?
I see.
Right. What you're saying is one way to solve it, but that's all like, again, additional memory and additional space, right? And also like, then you have to somehow synchronize them and things like that. So how can I keep track of those things? Okay. You should also keep in mind that when we do this counting, we'll lose some information, right? We're only keeping track of the top 100 relatively frequently, right? And later on, I might run into issues when I merge and so on. So, is there a more clinical way of coming up with this aggregating streams? Okay. And this leads to this really important abstraction. This is not just for streaming, but it's actually important in many database systems where I have an answer for one database, I have keeping some summary statistics for another database, and what I'd like to do is to kind of infer the summary statistics for the combined database. In this case, database like the stream, right? You're keeping something even succincter. Okay? So, abstraction. Sketching. Okay? So this is called sketching. Basically, what you do is somehow I keep track of information for one stream. Like, let's say searches in Texas, searches in California, right? So that's one stream, and this is another stream. And, I have my data structure, which is doing something. Let's say I run the Mr. Agrees algorithm on X, I run the Mr. Agrees algorithm on Y. Okay, so this is, let's say, searches in Texas, searches in California. So I'm storing only this summary statistic, right? Mr. Agrees on X, Mr. Agrees on California. And I do this for every state. Could I actually combine these summaries to actually compute the Mr. Agrees statistics on the whole stream? Right? Maybe I do it per state. Searches in New York. Okay? And I want to combine these things to get Could I do that? If I could do that, that would be great, right? Because somehow I only run the algorithms for the base units, but if someone comes at some point and asks, okay, maybe I'm interested only in Southwest. Then I just combine all of this, only the statistics, and get out what I would have gotten if I started out keeping track of that from the beginning. Okay, does it make sense? So if I can do this, then combining things is easy, right? I can always combine. Like for example, maybe I'll do Mr. Agrees for anime, TV, music, laptops, cameras, kids, and so on. And then someone asks for movies, I just combine those corresponding things. Okay? So loosely speaking, sketching is the following thing. Sketch. A data structure. So, I mean, I'm saying, again, this is all like, I'm using the word data structure as just whatever you store from the stream, right? We are storing this counter and array. So that's our data structure representation of the stream. We only store that portion, right? Computed in a streaming fashion is a sketch. It's called a sketch because you're storing some kind of caricature of the original stream, right? You're not storing the entire stream because it's too expensive. But then we also want some way to combine streams, okay? So if there exists a combining algorithm, okay, such that for all streams if I give you just the summaries of x and y for all streams x comma y, I can get out the stream, the summary statistic for the joint stream. Let's say I just concatenate this y at the end of x. Okay. You can ask for even more fanciful combining, but just start with that. So given the summaries, I can get out the summary of the concatenated stream. All right. If you have a structure like this, it's called a sketch. Make sense? So sketching is kind of the best form of answering streaming algorithms because then you just run it on parts and aggregating is very easy. Okay? And that's actually very important when you think of systems, right? All right. So next, what we're going to do is to design an actual sketching algorithm for frequency estimation, right? So Mr. Agrees is great. But unfortunately, it's not actually a sketch. There's no easy way to combine the summary statistics of different streams. You can try and do it, but it's kind of complicated and you'll realize that it's not the easiest thing to do. Okay? So that's the one drawback of Mr. Agrees, that somehow you cannot combine things easily. Okay? So what we're going to do next is to design a sketching algorithm for frequency estimation. Okay? All right. We are going to do this in an even more abstract and clean way. It's kind of surprising that everything turns out to be so nice, but it is possible here. So given a stream X, let Fx be the frequency vector. Right, so this is a vector which is frequency of okay. So you look at your stream and I look at the frequency of each item. That's some vector. I'll call that vector the frequency vector. Right? In some sense, my entire goal is to estimate entries of this frequency vector within some additive accuracy. Right? That's what we're trying to do. Given item 1, what is the frequency of 1? So like I point out to a coordinate and you have to tell me what is the value of that coordinate. Right? So we'll say a sketch or a data structure really is a linear sketch if whatever you store is a linear function of the frequency vector. Okay, so this is an important definition. Somehow we are introducing algebra to algorithms, right? So think of your algorithm. It is storing some statistics, okay? And what we're going to say is that whatever you store, think of it as a vector. If that is linear as a function of the frequency vector, that's a linear sketch. So ds of x is a some d-dimensional vector. For example, for Mr. Agrees, you can think of the data structure as a 2k dimensional vector, right? I'm storing k counters and k elements. It's some 2k dimensional thing. Okay? Is a linear sketch if ds of x is a linear function of the frequency vector. Okay. Let's look at an example and then it will make sense. Suppose I just keep storing the entire counts for each element. Okay, that's a huge, I haven't done any space savings, right? This should be times and not items. This is kind of a silly sketch because it's not doing any compression and just storing all counts. It's a hugely expensive space. It's very expensive in terms of memory, but it is a linear function of the frequency, right? Whenever I increase a count, this whole thing increases exactly by 1, right? Okay, so why would linear sketching be useful for combining? Suppose I had a linear sketch, right? Then at the very least, how can I combine things? Any ideas? So why is linear sketching actually a sketch? Like somehow, what is a combining algorithm for this?
With weight,
Say that again.
with weights that apply to the vectors in the dimensions.
Exactly, right? So somehow is going to be right. You had to put in some numbers, but I don't think that's too important. Okay, so let's say that they have same length. Then my claim is that the linear sketch of x and y I can get just by adding the sketches of x and y. Right? Because if you think of the entire stream, the frequencies are just getting added. Right? So the frequency vector of the combined stream is the frequency vector of x plus the frequency vector of y divided by 2. Right? Because I'm normalizing by the length, I increase the length, so it just gets divided by 2. Okay? So on the other hand, we know that ds, this is a linear function. So this implies that okay. So essentially, whenever I add something at the very end, it's as if I'm just adding vectors, right? Adding streams is just adding vectors. So the linear sketch makes everything just addition, numerical. Okay? I mean, intuitively it need not be, right? You might be storing some complicated binary tree or something, and then doesn't make sense to add data structures, right? But linear sketch is basically saying when I add streams, I just kind of add these numerical numbers and I'll get the summary statistic for the original thing. Okay? So that's a very desirable property, this linearity. And it's not just for this particular frequency estimation question, but often in streaming algorithms, linearity plays a very, if you can do a linear sketch, that's kind of like the holy grail. Somehow you can do addition, deletion, and all kinds of things just become numerology. Okay? All right. So now we at least know that if I have a linear sketch, I can do combining easily. But where do I get this linear sketch from? How can I get it? So let's ask that. So that's exactly what we're going to do next. We are going to give a simple linear sketch. Okay. We'll give a simple linear sketch which can solve frequency estimation. So remember that in the streaming algorithms, we have like these two steps. We process the stream, we store some data structure, and then you get queries, right? So linear sketch is basically solving sort of how you process the stream. Whenever I see the item, I keep updating this vector and I end up storing just this whatever d-dimensional vector, whatever your d is, right? And then when I get a query, I need to look at this vector and answer things. Okay? And linearity is only about the first part. Your query can be arbitrary. right? You can use all kinds of crazy things in your queries, but how you summarize the stream should be a linear function of the frequencies. Okay, does it make sense? Okay. So let's look at a sketch which is called the count min sketch. This is a sketch that's actually implemented on AT&T routers and so on. So it's a really influential sketch in practice. And this is due to Kormor and Muthukrishnan from 2005. So most routers have this sketch implemented as part of their mechanisms for detecting denial of service attacks. So I'm going to make a slight change in notation here, which is that, actually never mind, so let's not worry about that. And so the idea behind count min sketch is kind of a little bit like Mr. Breeze, but we're going to introduce randomness, and we are never going to decrease counters. All right. So what is this? So remember, we have these items coming one after the other, right? This is a stream, and you first pick a hash function. So you're picking a hash function which maps the namespace, item 1 is number 1, number 2, things like that, to k. K is a small number, right? I'm just storing some kind of a short hash of your entire name. Okay? And so you can think of it as basically, I have my hash buckets. Right, this is all items that are mapped to 1 by h. Okay, and this is bucket 2, bucket 3, bucket k. So the basic idea is somehow whenever I see x1, I'm just going to hash it at random. So maybe it ends up being here. X2 is another item number. So it's an element from 1 through m. I compute its hash. Maybe it ends up being here. X3 is something. It maybe goes here and so on. Okay. And instead of storing the number of times each item occurs, I'm just going to store the counts in each bucket. I only store how many items do I see, how many items got mapped to bucket 1, how many items got mapped to bucket 2, and so on. So it could be that x1 and x3, maybe the label A and label B both got mapped to the same element under hashing, right? Then the counts would be merged, but that's a risk I'm willing to take for now. Okay? So what is the count min algorithm? So let me, I'll keep this 1 here for now because it will become clear later. So first, you pick a single hash function which maps the namespace to k items. Think of it, k is 10, right? I'm mapping all IP addresses to just 10 elements. So presumably there will be a lot of collisions and things like that, but that's okay. And then I'll also introduce counters. C of 0, C of 1. C of 1, C of 2, up to C of k. So each CI is meant to count how many elements ended up in bucket 1, right? How many items in your stream had a hash value of 1, right? And this is the initialization, and for each item X in the stream, I need to increment one of these counters, right? So how do I increment the counter? Any ideas? I first compute the hash of that item, h of x, and I increment that counter. That's it. Okay, very simple item, just hashing and then counting. And this is how I process the stream, right? So my data structure is just going to be this k-dimensional vector of counts. So ds of x is just this k numbers corresponding to the counts. All right? And how do I answer queries? Someone comes and says, okay, can you tell me how many times the item A occurred? What is the frequency of A in the stream? What do I do then? What's a natural thing to do? Any suggestions?
Return the count at h of a.
Right. So return C of h of a divided by n. That's it. Okay, does make sense? And first claim, count min of 1 is a linear sketch. Can you tell me why it is linear? Well, it's almost really by definition, right? The hash function is fixed, and if I concatenate two streams, I'm just adding, right? It's the same version as the simplest algorithm that we had, where we counted all the statistics, right? Exactly. But now we're kind of grouping items into groups based on the hash and keeping counts per group. Okay, that's kind of one way to think about it. So we are adding counts hash is fixed before the string. Okay, you fix the hash function, you use a standard hash function in your Python library or something, and then you start adding things. Okay. Intuitively, what it's saying is, maybe, so let's say my hash function was doing something like this, right? So suppose, maybe 1, 3, 5, they all got hashed to 1. Maybe 2, 4, 6, 8, they got hashed to bucket 2. Okay, So that means from now on, every time you see the item 1, it gets counted into bucket. Item 3, bucket 1. Item 5, they all contribute to incrementing the counter, incrementing the first counter, right? It's as if for the counting algorithm, item 1, 3, and 5 are the same. Right? They'll always increment the counter, the first counter. Okay? Any questions about this? All right, okay. I mean, it seems like a silly thing to do. I'm combining items. Like, from now on, I'm going to say that all anime and TV, they got hashed to the same bucket. That would be a disaster, right?
Yeah, this seems like it's just like if I thought of this, I would just immediately be like, oh, this doesn't work. I'm going to try something else.
Right.
Right.
So the saving grace is randomness in the hash function. Okay. So the hash function is a randomized hash function, right? And if you think of any dictionary data structure or things like that, hashing plays a very important role, right? Hashing spreads things, and that's what saves us here too.
So we have to say that it works with high probability over a random hash function.
Exactly. So what's the guarantee? What can we expect here, right? And the first thing to understand is that this is a randomized algorithm, right? Because the hash function is random hash function. Okay. And what we're going to see is that in expectation, the behavior is pretty good, right? So so let's go back to what is this estimate, right? So this is my estimate for the frequency, okay? And we'll see, okay, so here the order is reversed. First of all, how can you compare f tilde a to the actual frequency? So what about the true count of an element versus what the algorithm returned?
It's at least the true. The estimate is at least the true frequency.
Right. So like here we're kind of overestimating things, right? We might overestimate things. I combined, iPad with whatever, Samsung Galaxy phone. That's a disaster. But like, from now on, the counts for both of them when I query will be higher than the true counts.
Mm-hmm.
Okay. So that, that's kind of, we combine items. Okay. So the next claim, which is a bit more subtle, is that the expected output of the algorithm, right? And remember that this is over the hash function. The hash function is random. Every time, this 1 through m, I group them at random. You can think of it as I'm splitting the namespace into k groups at random, and from now on, all the things in this group will contribute to one counter. All the things in this group will contribute to another counter, and so on. Okay? It's as if, I looked at all of you, I split you into 10 groups, and I said that, from now on, I just sum up all of your scores in group 1, group 2, and so on, things like that. Okay? And the claim is that this is, clearly this is at least FA, right? And you can show that it's at most so in expectation, it's giving you pretty much the same guarantee as Mr. Grease. Like there you're underestimating and you're proving a lower bound. Here you might be overestimating, but in expectation, you're not overestimating by too much.
So, but this is a guarantees for like if you just fix one element, right?
Yeah, for each A.
But on the other hand, I think it could be very likely that there's some element where the estimate is bad.
Right now, we'll see how to mitigate that soon.
Okay. I was just thinking of the case where there's like n-1 distinct elements of count, or like a bunch of elements. Oh wait, maybe that actually doesn't work.
So,
Or a bunch of elements that occur one time and then one element that occurs a lot of times.
mhm,
So if any one of the elements that occurs once gets grouped with the thing that occurred a lot,
right,
then its estimate is horrible.
right. But the thing is, for each item, per item, you're good.
But there will exist some items where it's bad.
Right. You can mitigate that to some extent, as we'll see.
Okay.
Yeah, we can mitigate that. That's why there's a count min 1 here and not count min. You'll see a more advanced version. So, okay, but let's look at what this is saying. In expectation for any item, you are doing pretty well. Your estimate is at least the true one and is at most 0.1 away or something like that. If you start with k being 10, and then you're only 0.1 away. Okay, so let's do the proof of this. Well, the proof is basically let's look at how many other items kind of collide with you, right? So so you have this m items, and there is your specific item A here that got hashed into some bucket, and the problem would be if many other items got hashed in here. If many other things also got hashed in here, then when you do the count, all of those would also contribute to your count, giving you a very high overestimate, right? So the idea is that the count C of h of A minus actual count for A is all things so all things which are not A but for some reason got hashed to the same bucket. Okay, so that's what we are looking for. So the difference between what the algorithm returns and the actual count is all other items which got hashed to your bucket, and you added up all of them, right? That's the exact difference that you have. That's the, if I'm looking for count A and item 1 also got hashed with me, meaning it collided with me, the hash collided with me, then its count got grouped with mine, right? So which is bad. But I can write this as something like B is not equal to A. So let's say NB, this is the actual number of times B occurs times whether or not h of B equals h of A. Okay? So I'm just writing it as an indicator that, okay, the hash collided and then I'm looking at the number of times B occur, right? So now I can do linearity of expectation. So let's look at the expectation, right? So I'm interested in the difference in the counts minus NA, what the algorithm counted minus the actual count is summation B not equal to A, and the hashes collided, right? But I can, expectation of sum is just sum of expectations, right? So I can write this as NB doesn't depend on the hash function, the number of times B occurred. So I just have the so what's the probability that you have a collision? What's the probability that hash of an item other than A gets, you collided with that? What is the chance of some other item getting mapped to where A landed?
1 over k.
1 over k, right? So you have k buckets, like if somehow I'm just throwing it into this k buckets at random, and I threw A somewhere, and what's the probability that some other item kind of, I throw it, magically it also landed in the same bin? It's exactly 1 over k, right? So this is summation B not equal to A and B times 1 over k, and I can say that this is at most n over k, right? The total number of other items is at most n. Okay? So you get that now you divide by n, so you get f tilde A is less than or equal to FA plus 1 over k. Great. Okay? So this gives us some guarantee on the expectation that my algorithm behaves well in expectation, right? But as we saw last class, when you're talking about randomized algorithms, just good behavior in expectation is not a sufficient guarantee in practice. You want to have some estimate of reliability, right? I'd like to know that, okay, I'm good in expectation, but can you tell me something about how reliable my algorithm is? Okay, suppose, for example, let's say the actual frequency is maybe 0.1, right? And I tell you that, well, okay, I gave you the example last time, but basically just getting right in expectation, even if you do that, most of the time you could be giving the wrong answer and still just be right in expectation, right? So suppose the actual frequency is 0.1, okay? And you ask me what's the frequency, and I tell you, oh, it is 0 with probability 0.9 and 1 with probability 0.1. So 10% of the time I'm going to say the answer is 1, that's the only thing I've seen. 90% of the time I'll say I haven't seen this item ever. Now in expectation, my answer is correct. But in reality, most of the time I'm giving a very bad answer. Right? So somehow I need to find a different way to do it. Okay? So how do I get an estimate on the reliability of my algorithm? I want to say something about how often or what's the probability that my estimate is very far from the truth. So what is the reliability? Okay. To answer this, let's look at something called Markov's inequality. So let's look at, what are we trying to say, right? I'm trying to understand what's the probability that, if I look at this f tilde a minus fa, my estimate is always higher than the truth, right? So this is non-negative number. I know that in expectation, it's at most 1 over k. If I think of k as like 10, it's saying it's at most 0.1 in expectation. But what's the probability that is higher than, maybe 0.2? What's the probability that is higher than some number, 0.3? How can I get that, right? So the way to do it is to use Markov's inequality. So let me say z is the random variable, f tilde a minus fa. Okay, so what do we know about z? Z is always non-negative because my algorithm only gives overestimates, and we know that the expectation of z is at most 1 over k, right? That's what we showed. The gap is at most 1 over k. Whenever you have this, Markov's inequality tells you an upper bound on your random variable actually being much bigger than its expectation. Okay? So in particular, we know that probability that z is more than 2 over k is at most a half. More generally, the probability that z is more than some t over k is at most 1 over t. Okay, so this means that basically the count min version that we saw is somewhat reliable. If I ran it with k is 100, then in expectation my answer is correct, and so together this implies that the probability that my estimate is bigger than this is at most a half. Okay, saying if I ran it with k is 100, the probability that my error is more than 0.05 is at most 50%. Right? I can also improve this. It's the same algorithm. It's just the bound is changing, right? If I want to, if I want to have smaller error, like smaller failure probability, then somehow my error increases. If I ran it with k is 100, then it's saying the probability that my estimate is off by 0.1 is at most 0.1. Like there's only a 10% chance that I make an error which is more than 0.1. Okay, and this is somewhat reliable, but in the next lecture what we'll see is how to boost this way beyond this half. Half is a very high number in terms of reliability. If I tell you, okay, my answer is going to be correct 50% of the time, AT&T is never going to implement it on the routers, right? Okay, you want much higher reliability for this to be usable in practice. Okay, and there are standard ways of boosting it, and we'll look at one of them, and that's where the min in count min comes from. Like so far we just counted things, right? We just hashed and counted. Okay, we'll talk about that in the next lecture. All right, see you all on Wednesday for the last lecture.
Professor?